The last thing you'd feel is a gentle pull, barely noticeable at first, like a tide coming in, except this tide is made of pure gravity, and it's coming from a point in space where matter has collapsed so completely that not even light escapes. You wouldn't see it coming. There's nothing to see, just a region of space where the rules quietly stop applying, and before your instruments could register what was happening, the physics would have already decided your fate. Not your ship, not your training, the physics. Because black holes don't negotiate, don't discriminate, and don't leave survivors. Every human who has ever lived, every machine we have ever built, every material science has ever discovered, none of it changes the outcome. You enter a black hole, you don't come back. Not because we haven't tried hard enough to engineer a solution, because the universe itself has made it structurally, mathematically, physically impossible. Black holes stopped being theoretical in 2019. That was the year the Event Horizon Telescope collaboration released the first actual image of one, a supermassive black hole at the center of galaxy M87, 6.5 billion times the mass of our Sun, ringed by a glowing disk of superheated gas. It looked almost peaceful in the photograph, a soft orange halo around a dark circle, but that image represented something chilling when you understood what you were looking at. You were seeing the last light that would ever escape that region of space. Everything beyond that dark circle, every photon, every particle, every unit of information, was gone, permanently. What the image told physicists wasn't just that black holes exist, it confirmed, in visual terms, that there is a place in this universe where our understanding of physics breaks down and where anything that crosses inside ceases to exist in any meaningful sense. We dream about black holes. For good reason. Science fiction has spent decades casting them as the ultimate adventure. Tunnels through space-time, shortcuts to distant galaxies, cosmic mysteries waiting to be unlocked by a brave enough crew. Christopher Nolan sent Matthew McConaughey through one and had him emerge with the secrets of a fifth dimension. Theoretical physicists like Kip Thorne have entertained the romantic notion that traversable wormholes connected to black holes might one day allow faster-than-light travel. Even serious scientists sometimes speak about black holes with a reverence usually reserved for things that give life rather than end it. And the curiosity is legitimate. These are the most extreme objects in the known universe. Of course, we want to know what's inside. The problem is that wanting to know and surviving the answer are two different things entirely. The destruction begins before you think it should, long before you cross what physicists call the event horizon, the boundary beyond which nothing returns. You would encounter tidal forces so extreme they have their own name, spaghettification. Here's the mechanism. Gravity weakens with distance. That's always true, everywhere in the universe. But near a black hole, the difference in gravitational pull between your head and your feet becomes so extreme, so rapidly, that your body doesn't experience gravity as a uniform force. It experiences it as a stretch. The side of you closest to the black hole gets pulled dramatically harder than the side farthest away. Your body begins to elongate. Then it elongates more. Then the differential forces exceed every molecular bond holding your tissue, your bones, your cells together, and you are pulled apart at the atomic level into a long, thin stream of particles spiraling inward. For a stellar mass black hole, the smaller variety, perhaps 20 times the mass of our Sun, this process would begin well outside the event horizon. You would be torn apart in open space before you even reached the point of no return. The spaghettification of a human body wouldn't take long. We're talking fractions of a second. One moment you exist, the next you are a ribbon of plasma. Supermassive black holes introduce a different horror. Because they are so incomprehensibly large, millions or billions of solar masses, the tidal forces at their event horizons are actually more manageable. You could theoretically cross the event horizon of M87's black hole intact. Your body would survive the transition, your instruments might still function, you might not even feel anything unusual in that precise moment. And that is the cruelest trick in the universe, because the moment you cross that threshold, your survival is already over. You just don't know it yet. The event horizon is not a wall. It has no surface. It is a mathematical boundary, a point of no return defined purely by geometry and escape velocity. Once inside, every possible path through space-time, every direction you could travel, every trajectory your ship could take, leads deeper in. Not toward the center necessarily, but in W's. The universe outside becomes inaccessible not because something is blocking you, but because the shape of space-time itself no longer contains a path that leads out. You aren't trapped by a force, you are trapped by geometry, and geometry cannot be engineered around. Time compounds this. From an outside observer's perspective, something strange happens near the event horizon due to gravitational time dilation. As you approach it, you appear to slow down. Light from your ship gets stretched, redshifted, dimmer. To someone watching from a safe distance, you appear to freeze at the horizon, your image fading over astronomical timescales. But from your own perspective, you cross quickly, seamlessly, with no dramatic fanfare. The disconnect between those two realities, what an outside observer sees and what you experience, is one of the most disturbing features of general relativity. It means there is no rescue. Even if a ship tried to pull you back at the last possible moment, they would watch you appear to hover at the threshold for what looks like billions of years while you experience seconds. Communication becomes impossible. Coordination becomes impossible. Physics has already separated you from the rest of the universe. Then there is the radiation. Astrophysicist Stephen Hawking demonstrated theoretically that black holes aren't perfectly silent. They emit what's now called Hawking radiation, a quantum effect at the boundary between inside and outside. But this radiation isn't a gentle glow. Some theoretical models, particularly the firewall hypothesis proposed in 2012, suggest that the event horizon of an older black hole might actually be lined with a wall of high-energy radiation, a firewall, that would incinerate anything crossing it instantaneously. The firewall hypothesis remains debated, but the underlying physics it responds to is not. The information paradox, what happens to the information content of everything that falls into a black hole, is one of the most unresolved problems in modern physics. And every proposed solution involves consequences that are catastrophic for anything attempting to survive entry. Either you are incinerated at the horizon, or your quantum information is scrambled beyond reconstruction. There is no scenario in the theoretical literature where you emerge intact. Beyond the horizon, assuming you survive the tidal forces and the radiation, you are now falling toward a singularity, a point of infinite density at the core of the black hole where our mathematics produces results that no longer correspond to physical reality. We don't know what happens at a singularity because our current laws of physics break down there. General relativity and quantum mechanics give contradictory answers. But what we do know is this: the singularity is in your future, inescapably. The way the future is always in your future. Every path you take leads there, and the time it takes to reach it from the moment of crossing the event horizon, depending on the black hole's size, ranges from microseconds to perhaps a few hours. During that time, tidal forces continue to increase, radiation continues to intensify, and at the singularity itself, the mathematics suggests density becomes infinite and volume becomes zero. Whatever was left of you ceases to exist as a coherent physical structure. What happens next is not something physics can currently describe, but survival is not among the proposed outcomes. These forces don't line up politely and take turns, they cascade. The same gravity that drives spaghettification also accelerates you toward the singularity. The radiation environment intensifies as you fall deeper. Any heat generated by the compression of infalling matter adds to an already lethal thermal environment. Your ship, if it somehow stayed intact longer than your body, would face the same tidal stresses, the same radiation, the same inescapable geometry. Material science has theoretical limits. No known or theoretically possible material has the tensile strength to resist the tidal differential forces near a stellar mass black hole's singularity. No shielding absorbs the full spectrum of radiation in that environment. No propulsion system generates the energy required to escape, because escape is not a matter of thrust. It's a matter of exceeding the speed of light, which is not possible under known physics. Not for a spacecraft with mass. This is not pessimism dressed up as science. This is what the equations produce when you put the numbers in. Black holes represent a region of the universe where the laws of physics, as we understand them, don't offer a survival mechanism. Not today, not with our current technology, and not with any technology that operates within the physics we know. The gap between what science fiction imagines and what the mathematics demands isn't an engineering problem. It's a fundamental one. What remains after all of that is something worth sitting with for a moment. We have never sent a human anywhere near a black hole. The closest one to Earth, a stellar remnant called Gaia BH1, is roughly 1,500 light-years away, and yet we know with precision what would happen to you inside one. We calculated it, we derived it, we photographed the edge of one from the other side of the galaxy and matched the image to our predictions with extraordinary accuracy. The human mind reached across 1,500 light-years, across 27,000 light-years to the galactic center, across 53 million light-years to M87, and came back with correct answers. We cannot go there, we may never go there, but we understood it. In a universe that has no particular obligation to be comprehensible, we found comprehension anyway. That's not nothing. That's almost everything.